Okay, now we are going to study power distribution. And in this lesson, we're actually going to take a little field trip out to Schneider Electric, where I work, and look at power from the pole all the way down to a plug. So I hope you enjoy this lesson. Let's get to the presentation. All right, like I said in the intro, we're actually going to take a field trip out to my place of business at Schneider Electric, and we're going to study the power as it's distributed from the pole all the way down to the plug. But before we did that, I thought I'd tell you just a little bit about my company and my office here in St. Louis. I work for Schneider Electric, and we are actually located in O'Fallon, Missouri, very close to the intersection of Highway 64 and K. And if you're not familiar with Schneider Electric, you might be familiar with some of our brands. Our largest brand is Square D. Lots of people have heard about that, and big player in the electrical industry. Modicon PLCs, that is a product of ours that does very, very well. That's what I program. And American Power Conversion, better known as just APC, is the company I actually went originally to work for, but very quickly was acquired by Schneider Electric. And they're best known for their uninterruptible power supplies. Some people call them UPSs for the IT industry. But this building here is our Technical Learning Center. And in the front is a whole customer experience that they can go in and look and test or demo products that we make, and get a feel for the suite of products that we make, because we own a lot of companies and make a lot of different products. And in the back is a lab where we test new products. I'm in the new product development group, and I get to test all sorts of the products that we developed. So of the products, Schneider Electric makes things such as push buttons, circuit breakers, relays, time delay relays, motor starters, variable frequency drives, and like I said, programmable logic controllers and the software that goes along with it. So I get to work with all that equipment and have enjoyed doing that for 11 years. This is out back behind our building, and this is the outer road to Highway 64 right here that van is driving on. And these are the power poles that are running along the outer road, and they are at a potential of 34,500 volts. And that gets fed into a sub-pole that is exclusively for our building, and it takes these poles, these lines that are on the pole, and feeds them into the ground for them ultimately to come up in my substation. Here is the substation. This is the parking lot of that building you saw in the beginning there. This is the parking lot out back, and this is my substation. We have a nice concrete wall to protect it and protect the public and employees from any issues that we would have. And that 34,500 volts you saw go into the ground comes up right here and gets distributed over to a step-down transformer here that takes that 34,500 volts and steps it down to 12,470 volts. Now this is also some switchgear that a UE can actually disconnect us from their service right inside this substation here. This transformer is an oil-cooled transformer, and you can see some fans here that blow on that. But that 12,470 volts ultimately gets fed back into the ground and goes underneath the building and comes up inside the building. So we're going to go to a video inside the building and look at the transformer we're actually going to study there, which is going to step down the voltage from 12,470 volts down to 480 volts. So we'll see you inside. Okay, now we're inside, and what we saw outside at the substation stepped down my 34,500 500 volts to 12,470 volts, and then fed it into the ground. Comes underground into the building and comes up inside of this step-down transformer. This step-down transformer takes my 12,470 volts and steps it down to 480 volts, and then it is distributed throughout the building. Now, as you can probably hear on the microphone, it has quite a loud hum, and I'm at a very low load right now. I'm here very early in the morning, and I'm only pulling about 170 amps per phase on the 480 volt side. This transformer can do up to 1,000 amps on that 480 volt side. But one of the things that we have to be concerned with is the temperature. I mean, as you can see here, I'm running between 100 degrees C, 85 to 100 degrees C on each phase in this transformer. I'm going to bring the camera in a little bit closer. We're going to look at the nameplate. We're also going to look at another product that we have installed on here that we make at Schneider Electric that makes it possible for people to analyze the performance of their transformer. So we'll be right back. Okay, here we are at the nameplates, and as you can see on the nameplate, this is a Square D step-down transformer. We use all of our own products here in the building, and this is a delta to Y transformer. We'll get into that in the presentation. But below that, we have installed a product that we make. It's an infrared window, and what this allows us to do, and our customers to do, is to remove this bezel, and you can take pictures with an infrared camera, and what that can do is tell us hot spots or cold spots on the coil, and if there is an issue where we have to go in and do some preventive maintenance, or if it's a predictor for possible failure. So it's a real good product for us. It's really helped improve safety in the electrical industry, and we use it on all of our transformers here. We are going to go to the presentation now and learn a little bit more about delta to Y step-down transformers. We'll see you over there. Okay, I hope you enjoyed the video there. We are now looking at a close-up of the nameplate. And like I said in the video, this is a Square D product that we're looking at. And there's a lot of information on the nameplate. We're not going to get into everything here, but what I wanted to point out is on the nameplate, it tells me that I'm going to be stepping 12,470 volts down to 480 volts. And this should pique your curiosity a little bit. It says 480 volts, and then it says Y behind it, and then it says 277 volts. And we'll talk about that as we get further into the lesson of what that actually means. So let's draw a schematic of what's going on inside there. So here's a transformer. We have a mechanically coupled transformer. My two vertical lines there show me that I'm mechanically coupled. I have a primary side, and my primary side I'm calling my high voltage side. The NEC depicts any voltage higher than 600 volts to be considered high voltage. And since we are dealing with 12,470 volts, that is considered high voltage. And then our secondary side here is our low voltage side. It is below 600 volts or less. And so it is considered low voltage, so that is our low voltage side. And I've just denoted here we're stepping down 12,470 volts to 480 volts. Now I'm going to polarize my transformer. And what I'm doing here is denoting one side versus the other. So I'm going to use the terminology the polarized side versus the non-polarized side of my transformer. So I use the dot to denote the polarized side, and I'm going to do that on my secondary winding as well. That, along with our phase letters, will be one of our phase windings. On our primary side, I will use capital letters. So this is phase A, so I denote it with a capital A. And on the secondary side, to denote that it is the secondary side, I use a lowercase a. That comprises my one phase of my three-phase transformer. So I'm just going to quickly put up my other two phases here. But you know that they are denoted similarly as we were in phase A. Now, this side, I said in the video that this was a delta to Y transformer. We're going to get into that a little bit more. I'm going to go ahead and connect my primary up in delta. So I'm going to take my non-polarized side of phase A and I'm going to connect it to my polarized side of phase B. Okay? And I'm going to take my non-polarized side of phase B and I'm going to connect it to the polarized side of phase C. And I'm going to take my non-polarized side of phase C and connect it to my polarized side of phase A. And that puts me in a delta connection. It's a little difficult to see here, so I'm going to show a little graphic that is denoting the same connection that we have here, only in a triangle fashion. And if you're familiar at all with Greek letters, there is a Greek letter called delta that is a triangle in shape. And this is considered a delta connection because it is triangular in shape. So my A phase is going to be between H3 and H1. And if you look between H3 and H1, there is my A phase. And my B phase is going to be between H1 and 2, which we see here. And my C phase is going to be between H2 and H3. And this is a little snippet of the faceplate, and it shows the exact same configuration. It shows H1, 2, and 3 for my three connections there for my delta. Okay, let's go to my secondary side. I'm going to connect my secondary side up in Y. So I have 3 points here that are the same point electrically, but I'm going to take those 3 points and I'm going to ground them. I'm going to reference them to ground. And we'll see the benefits of that a little bit later. And I am going to denote the ends of my lines here with X1, X2, and X3. And this is a little difficult to see in the Y configuration. So I am going to, X0 I have for my ground down here. So here is my Y connection that I'm showing is the exact same configuration here. So X1 to X2 comprises A and B. So this would be my A phase and this would be my B phase. Okay, X2 to X3, X2 to X3, this would be my B phase and that would be my C phase. And they're connected in Y, and this dotted line denotes that it is grounded, and they are labeling the ground X0, which I have shown here. This is a snippet from the nameplate that is showing the exact same thing. X1, 2, and 3 are in a Y configuration. Now this point here is electrically the same as this point here, so I'm just moving my labels out to the ends of the lines just to clean them up. And then we'll look at a snippet of the nameplate that shows the H1, 2, and 3 as 1, 2, and 3 are the same points there. And X0, which is my ground, is here. And then X1, 2, and 3 are labeled right there. So, looking back at the nameplate, here is that snippet that I brought and showed the delta connection, and here is the snippet of the Y connection. So that is going to help us when we see nameplates on transformers, how to read them properly. The other thing I wanted to note here is we see now why it said 480 volts Y. Okay, so at least that portion of it we understand. We still are trying to figure out why does it say 277 here. We'll get into that in just a moment. But we know that this is a Y, denoting that our secondary side is a Y connection. The other things that I want to note on here is my 12,470 volts has a abbreviation of HV for high voltage, which we talked about on the previous slide, and my 480 volts is my low voltage side. Okay, so now we are back and we need to get some more terminology and down before we start talking about voltages and currents. So a phase is anything between windings on the transformer, okay? So a phase means across the transformer windings, okay? And a lot of times this is very easy to get confused, phase and what we ultimately call a line. So here a phase is denoted by the voltage across this phase would be denoted V phase and a capital letter A, because we said the primary side we're going to use capital letters. And just to denote the different sides of the windings from the polarized to the non-polarized, I'm putting a plus and a minus sign. And I'm going to do the same for the other two phases here. And on the secondary side, there again, I have a phase that is from this polarized side to the non-polarized side, and I denote that V phase with a lowercase letter a. And I am denoting the polarized side with a positive sign and the non-polarized side with a negative sign. And I do that for all three phases. Now we're going to learn another term here, and that is line-to-line voltage. Okay, and this is what I was saying. Some people get phase and line-to-line voltage confused, and there's a good reason for it, and we'll get into that here in just a minute. So line-to-line voltage is voltage across two lines. It sounds too simple, but we're going to learn, depending on the configuration of the transformer, it is an important distinction to note. So my line-to-line notation will be V sub LL, and then in this case lowercase ab, because I'm going from my A polarized line to my B polarized line. And same for my line-to-line voltage from B to C, because I'm going from my B polarized portion to my C polarized portion. And same thing for C to A. Okay. Now let's look at the relationship between phase and line to line. Well, let's finish denoting this here. So I've denoted over here that my V line to line capital AB, and if I take a measurement here of my line to line on my primary side, my delta connected side, is that going to be different from my phase voltage, my V phase A? Well, let's look. This point all along here is the same point electrically, okay? And this point all along here is the same point electrically. So here, my voltage will equal my voltage that I have here. So I can say that V line to line AB is going to equal V phase A. And this is for my delta connected primary side. Here is my V line to line B to C. And if you look, same point electrically here on my polarized side of my B phase, and my non-polarized side of B phase is the same point electrically as my H2, so my line to line will equal my phase, and the same is true for C. My polarized side of C is the same point as this line here, and my non-polarized side of C is the same point as right here. So we can make a statement that for a delta-connected transformer, the voltage across two lines shall equal the voltage of the phase winding. Now that is true for a delta-connected transformer. And now this is why in the field people do get confused between line-to-line voltage and phase voltage. And that's why it's important to be able to read the faceplate on a transformer, and it's important to know how that transformer was connected. So here is the formula for this statement right here. My voltage line to line is going to equal my voltage of my phase. Okay. Let's look on my secondary side. Remember, we're connected in Y, so it will, or it may be different. And we don't want to assume anything here. So I'm going to measure my line-to-line voltage here. And I'm going to measure my phase voltage here. Are these going to be the same? Well, let's look at this. It's the same point electrically here, right? That works out. That's the same point electrically. Let's look at this point here. Is this point the same point electrically as this point? No, it is not. This point is, in essence, ground. This point is the the polarized side of secondary phase B. So they will not equal one another. But we do have a way of determining or calculating between these two. For a balanced Y connected transformer, the phase voltage shall be equal to the square root of 3 times the line voltage. Let's look at the formula for that. It's easier than reading the English portion. So my phase voltage will equal the square root of 3 of my line voltage, or my line-to-line voltage. Now, there is one caveat in this statement, and it's right here. I've italicized it. This is for a balanced Y transformer. And what a balanced Y transformer is the load across here to here, the load across here to here, and the load across here to here are equal, meaning that we have the same current running in all three of those lines. And that is rare. But for conceptual principle and for, just for learning sake, this is an accurate statement, and it helps us to understand the relationship between, on a Y connection, the relationship between the line-to-line voltage and the phase voltage. So here, if my line-to-line voltage is 480 volts, we already know that because that's what the nameplate is telling us. We need to figure out what the phase voltage is. So if we take the phase voltage is going to equal my line voltage times my square root of 3, and that's going to equal 277 volts. Now, if you remember in the nameplate, it showed the low voltage side as a 480Y/277. And that's what that 277 means, is my phase voltage is at 277 volts, even though my line voltage is at 480 volts. And of course that's true for all three phases. Again, that is for a balanced Y transformer that we can use this formula. We get into phase angles and vectors and things like that if we're not balanced, and we're not going to get into that today. We just want to understand the concepts of this. Okay, we're going to talk about current now. And some students get confused with current. When we're talking about alternating current, they're saying, how can you say that there's a direction to the current when the current is actually alternating? Well, the best way for me to think about it, and I think the best way to explain it, is to look at where you're coming from and where you're going. So the switchgear that I have out in my parking lot And the power panel that I am using to distribute all of my 480 volts there's going to be an obvious direction there. I'm going to be consuming current from here to here. So ultimately, my current is going to be flowing in this direction. So that is the way that helps me understand we're talking about current flows in that direction from my source to my consumer. So let's start on the secondary side this time. We're going to denote current on the secondary phase A as I for current, sub L for my line current of phase A with a lowercase a. We're going to do the same thing for B and for C. And then for my phase, I'm going to say I for current and use my phase symbol and a lowercase a, and do the same thing for B and for C. Now let's think about this for a minute. If I take my Fluke 3000 here and I take a measurement of this secondary phase A line current, and I take my same Fluke 3000 and I throw it on my phase current here, are they going to be equal? Well, is there any branch circuits in here? Is there anywhere for the current to flow other than the same current to flow through each meter? There is not. So I can easily say that my line current for phase A equals my line current for the secondary A line is equal to my phase current for the A secondary phase. And if that is true for phase A, it is true for phase B and for phase C. So for a Y-connected transformer, the line current shall be equal to the phase current. And we can just simplify that with this equation here, that the phase current equals the line current. Let's go on the primary side and see if the same holds true. Okay, so first we're gonna denote the primary side with a capital A, but we're going to say my line current I sub L, capital A will be denoting my line current, and the same for my B line and my C line. And then I have my A phase current, my B phase current, and my C phase current actually going through my phase windings. Okay. So now if I take my Fluke 3000 and I throw it on the A line, and I take a Fluke 3000 and throw it on my A phase, am I going to be reading the same current? Well, remember Kirchhoff's current law? We have a node here, right? H3, that's a node. And Kirchhoff's current law says that the sum of the currents into a node has to equal the sum of the currents out of the node. So I have a current flowing into this node here, okay? And my A phase current is going to be flowing out of that node. But do we have a branch here? We do. We have another current, this C phase current, that is going to be flowing in this direction. So we have two currents flowing into that node, and we have one current flowing out. So could it be possible for my A phase current to equal my A line current? Well, Kirchhoff's current law says that that cannot happen. So let's look at, I have that current there that I have to be concerned with. That's what I'm showing with that meter. So I have to apply Kirchhoff's current law here. I have to say the sum of my currents into a node has to equal the sum of the currents out of the node. I only have one current out of this node, but I have two currents into that node. So that's why I'm saying the sum of those two currents are equal to the phase, my phase current. And that is true for both line B and line C. So we can make a statement here that is also true. For a balanced delta connected transformer, the line current shall be equal to the square root of 3 times the phase current. Okay, again, this is for a balanced a delta connected transformer that is balanced. So my I line current equals the square root of 3 times my phase current. Okay, and again, if we get out of balance, we're going to have to look at vector diagrams and things like that we don't want to get into today. Okay, so if that is true, then for my line current on line A is going to equal the square root of 3 times my phase current. And for line B, square root of 3 times my B phase current, and for line C, the square root of 3 times my C phase current. Now, as I promised, this breaker panel here is a breaker panel inside my lab. And so here's the panel that US1 step-down transformer feeds. And it is a 480 volt transformer. And inside it has a breaker for my welder in my lab. So that's the breaker right there. And as you see the large size here, because that's a 3-phase breaker. It's actually across 3 different phases there for the connection to the plug. So that's my welder. And here's my MIG welder that I have in the shop. And that's the plug that we're actually heading towards. And there's a picture of the plug. And this even says what poles that those phases are on. And the plug here is connected to phase A, and I'm showing lowercase a because we're on the secondary side, phase A, B, and C. And that is from the power from the pole all the way down to the plug at Schneider Electric in O'Fallon, Missouri. So I hope you enjoyed that lesson. This is part 1 of a 2-part series. We will do another one where we will talk about phasor diagrams and when we do have an imbalance within our system. So we'll see you then.